everyone, I'm İklim Yoran. I will now present you my EEE 474 term project. For my term project, a selective excitation pulse design is performed using case-based interpretation of small-tip angle approximation. Firstly, the derivation for transfer magnetization stemmed from selective excitation pulse and required parameter equations were obtained to design excitation pulses. Small-tip approximation and Fourier transform between case-space and spatial domains were used to derive the useful equations, and certain assumptions for parameters are done. The main objective of the project is to develop two types of pulse design as pencil beam and rectangle shaped, and simulate them using MATLAB. As the first phase of the project, I evaluated the small-tip angle approximation in case space and obtained this transverse magnetization equation. Then I defined a new variable as k of t and rewrote the interpretation as written here. And as you can see, it's the Fourier transform of weighted case space by RF excitation B1 of t. As the second phase, in order to start designing a 2D selective excitation, first we need a spatial frequency weighting function, d of k. The Fourier transform of d of k will give the localization we want. For the pencil beam shaped excitation pulse design, we will define a circularly symmetric Gaussian localization excitation. Thus, d of k will be circularly symmetric Gaussian function as well. Here we can see the equation, and we will use this equation to choose parameter beta and a. So for the third phase of the project, I've designed excitation pulses. So first one is pencil beam shaped one. To design the pencil beam shaped excitation pulse, we need some parameters. And for this pulse design, I need to cover 95% of the area. So using the d of k equation and Fourier transform, I could come up with this equation and I get the beta parameter like this. Similarly, I could obtain the a parameter from d of inverse Fourier transform of the d of k. Field of view is set to 10 centimeters, and we could get the n parameter from the equation shown here. So the maximum gradient amplitude is 4 and the peak amplitude becomes 2, and therefore we could obtain the t parameter as 4.64, and using this equation we could obtain the gamma values for the different flip angles as we said before, pi over 2 and pi over 6. B0 is 3 Tesla and slew rate is approximately 13,000. So as the fourth phase of the project, rectangle shaped pulse design is made. The hardware limitations are same with the previous design. For this rectangle shaped pulse design, a rectangle of fx is equal to 1 centimeter and field of view y is equal to 10 centimeter is excited. Maximum gradient is again 4, and the gx and gy gradient design and their durations are calculated according to this equation. For B1 RF pulse design, sync coefficients are used to weight sync pulse, which has the same with plotty of gx. Unfortunately, for the term project, the MATLAB simulations were not successful, but the designs are pretty accurate. Thank you for listening.